Hello everyone and welcome back to Master 20A Mathematical Logic. Lecture 5 Formal Proofs. In this lecture we begin working towards the proof of Gödel's completeness theorem, which states that any universally valid L formula may be obtained using a finite deduction or a formal proof. This fundamental result establishes a perfect correspondence between semantic truth and syntactic probability in first-order logic. Today we begin by formalizing the notion of proof. Definition: by the logical axioms we mean the following universally valid formulas: A, first order tautologies, B, the equality axioms, E1 through E5, and C, the quantifier axioms, Q1 through Q3, all introduced in the previous lecture. So the formulas in the first group, in group A, the first order tautologies, are those first order formulas that can be obtained from propositional tautologies by substituting some first order formulas instead of their variables. The equality axioms give a list of universally valid first order sentences that express that the equality operation is a congruence relation, that is an equivalence relation, which is compatible with the functions and the relations of the language, and C, the quantifier axioms, which list a collection of universally valid formulas that express the properties, the basic properties of the existential and the universal quantifier. So all of this combined we'll refer to as the logical axioms. Next, we define the deduction rules. There will be only two deduction rules. The first one is the modus ponens rule. From phi, and phi implies psi, where phi and psi are first order formulas, one can deduce the formula psi. And the second rule, the generalization rule, which says that from phi one can deduce the formula for all x phi, where x is any variable. We will typically abbreviate the modus ponens rule as MP and then the generalization rule as gen. Given the logical axioms and the deduction rules, we can now define formal proofs. 1. Let phi be an L formula in some given first order language L, and let T be an L theory remember, this just means that T is a set of L sentences. Then a formal proof of the formula phi in T or from T is a finite sequence of L formulas phi 0, phi 1, etc. through phi n for some natural number n, so that the last formula in this sequence, phi n, is equal to phi, and such that for every I less or equal than n, we have that either the corresponding formula phi I is in T, or phi I is a logical axiom or it can be deduced by the modus ponens rule from some formulas phi j and phi k that already appear earlier in the sequence. So with j and k both strictly less than I, or it can be obtained by the generalization rule of deduction from a formula phi j for some j less than I. And 2, we will say that a formula phi is provable in T, which will be denoted symbolically as T is provable in phi subscript L, denoting the language of the formula and the theory, if there exists a formal proof of the formula phi in T. Finally, we will write provable phi without specifying the theory T in the case when phi is provable in the empty theory. What is the intuition behind this definition? The idea is that we first specify the logical axioms, which represent a simple collection of universally valid formulas that are self-evident, that evidently hold in all first-order structures. And then we specify some minimal, simple set of deduction rules. Well, minimality is a separate question, but we specify some very simple set of deduction rules, just 2 deduction rules, which again, as we will see soon, preserve universal validity. And then we will say that the formula is proved, has a formal proof from a given theory, if we can deduce it applying only these fixed deduction rules, infinitely many steps, from the logical axioms plus those axioms that are included in the theory T. Remark: a priori, the relation of formal probability depends on the language L, in which the formula phi and the theory T are considered, since if we take a larger language, so let's say if L prime extends L, then there are more proofs in the language L prime than in the language L. However, we shall see in the future that the relation of logical consequence is equivalent to the relation of formal probability in a given language. That's the content of Gödel's completeness theorem, which will show a posteriori that probability of a formula does not depend on the language in which it is being considered. But until we arrive at this point, we will keep the subscript L according to our formal definition. Let's consider some examples of formal proofs. 1. If phi and psi are two L sentences, then we have that the theory T consisting of these two sentences, phi and psi, proves the conjunction phi conjunction with psi. For the next examples, we assume that phi is an L formula, x, y are variables, and T is an arbitrary L term. Then we have the following probability statements. First, we have that the formula for all x phi implies phi with T substituted in the place of x is provable. 3. If the variable y does not occur in the formula phi, then the formula for all y phi with y substituted in the place of x implies for all x phi is provable. And finally, 4, we have that the formula for all x phi implies phi is formally provable. Let's demonstrate these claims by establishing formal proofs in each of the cases. 1. So we have to exhibit a formal proof for this. So we can take phi 0 to be the formula phi itself. We can take phi 1 to be the tautology. Phi implies psi implies the conjunction of phi and psi. Now, applying the modus ponens rule, we deduce the formula phi 2, which we take to be psi implies phi and psi. So here we are applying the modus ponens rules to phi 1, split into two parts. The first one is phi, and the second one is this whole implication formula. Now we can take phi 3 to be the formula psi itself, and we can apply the modus ponens rule to phi 2 using the axiom psi. So by modus ponens we get phi 4, which is the conjunction phi and psi, which is exactly what we wanted. In the future we might not list all of the formulas phi 0 through phi n in the formal proof, but rather use the previously proved formulas as axioms. Let us prove 2. First of all, recall that the formula for all x phi is just an abbreviation for the actual formula not exists x, not phi. So hence this will be the actual formula we are using here. Then the formal proof is the following. We take phi 0 to be the formula not phi with t substituted in the place of x implies exists x, not phi. Now this is a logical axiom, a tautology. By the quantifier axioms, namely by Q2, we take phi 1 to be the formula consisting of the following implication. So the first part is not phi with t substituted in the place of x implies exists x, not phi, implies not exists x, not phi, implies phi with t substituted in the place of x. This formula is a tautology because we can consider the propositional formula not p implies q, implies not q, implies p, and we substitute the corresponding formulas in place of these propositional variables. And finally, phi 2 equals the formula for all x phi implies phi with t substituted in the place of x, which we obtain by the modus ponens rules applied to the formulas phi 0 and phi 1. Let us provide a formal proof for 3. So the formula for all y phi with y replacing x implies the formula phi with y substituted in the place of x, and then substituting x in the place of y is an instance of case 2 with the formula phi with y substituted in the place of x in the place of phi in the statement of 2. As we also discussed earlier, by the rules for simultaneous substitution, we already know that the formula phi with y substituted in the place of x, to which we then apply the substitution x in the place of y, is simply equal to the formula phi. Hence, we get the formula for all x, for all y, phi with y substituted in the place of x implies phi. By generalization, i.e. we can always add universal quantifier in front of this whole formula. Now by Q1 we have the following universal formula for all x, for all y, phi, y, substituting x implies phi, implies, now let's be careful, so this is the first formula of the implication and this is the second one in the quantifier axiom. So then this implies that for all y, phi, y, substituting x, implies for all x, phi. And note that here it is important that y does not occur in phi. This is a requirement in the first quantifier axiom, Q1. And now, by modus ponens, we deduce the second part of this implication. So we deduce for all y, phi, y substituting x implies for all x, phi, which was indeed the desired formula in item 3. And finally 4 is a special case of 2. Since by the rules of simultaneous substitution, we know that phi is equal to phi with x substituted in the place of x. And so this concludes the proof of all the cases in the example. Next, we're going to show that the formal proof system that we have defined is sound, which means that if we're given a theory T in the language L, and phi an L formula, then if the theory T proves the formula phi, then also T has phi as a logical consequence. So here we have a syntax of formal probability on the left-hand side, and we have logical consequence or the semantical consequence on the right-hand side. Proof. We know that the logical axioms are all universally valid because they are first-order tautologies. Hence, they hold in all L structures. We also have that if phi is a logical consequence of T and phi implies psi is a logical consequence of T, then also psi is a logical consequence of T. So this follows simply from the definition of satisfaction of formulas and structures. Let's just remember what this means. So the logical consequence means that for any structure A which satisfies T, so for any model of the theory T, by the definition of logical consequence, we also have that this structure A must satisfy the formula phi, and by the second part of the assumption, we also have that A must satisfy phi implies psi, but of course the implication is just an abbreviation, and by the definition of truth we see that also A must satisfy psi, and this holds for any first order structure A which is a model of T, so which tells us that psi is indeed a logical consequence of T. Similarly, from the definition of satisfaction of formulas and structures, we have that if phi is a logical consequence of t, then for all x, phi is also a logical consequence of t. So we see from these two observations that each of the deduction rules, the modus ponens and the generalization rule, preserves the property of being a logical consequence of a theory, hence we can conclude the proof of the lemma by induction on the length of a formal proof of phi from t, where by the length we mean the obvious parameter, so the length of a formal proof given by the sequence of formulas phi1, phi0 through phi n is n plus 1. Next, we define several properties of first-order theories. So let T be an L theory. We will say that T is inconsistent if there exists an L sentence phi such that both phi is provable from T and the negation of phi is provable from T. We will say that T is consistent if it is not inconsistent. And we will also say that the theory T is complete if it is consistent and for any L sentence phi, we have that either T proves this sentence phi or T proves the negation of phi. Let us consider a couple of examples. First, assume that A is an arbitrary L structure then we can consider the following set of first-order sentences. We denote it as the theory of A, and it consists of all L sentences phi so that A satisfies phi. So all L sentences that are true in phi. So this is, of course, a theory. It's a collection of sentences. And refer to it as the theory of the structure A. Sometimes we call it the complete theory of A, because indeed it is complete. Simply because for every sentence and the definition of satisfaction in the structure, it either holds in the structure, and if it doesn't, then its negation holds in the structure, so it's complete, and it is also consistent. And it is consistent by soundness of formal probability. Because by soundness, if T proved both phi and not phi, then both of those sentences would also have to be satisfied in the structure A, which is impossible. 2. The theory of algebraically closed fields is the theory in the language of rings, so L-ring theory, which we denote as ACF for algebraically closed fields, and it consists of the fields axioms which we already know can all be expressed in first order together with a sentence chi n for each natural number n greater or equal than 1, expressing that any polynomial in one variable of degree n has a root, which is exactly the definition of algebraic closeness of a field. So we can write this sentence as chi n, for example, as follows. So we say that for all z0 through zn minus 1, which are going to represent the coefficients of the polynomial, there exists x such that x to the power n, which you should think about it as an abbreviation for the expression x times x times x n times, which is indeed now a term in the ring language. So we have that xn plus z n minus 1, x to the power n minus 1 plus etc. plus z0 is equal to 0. This is indeed a sentence in the language of rings, and it expresses the desired condition. We have the following remark. First, an L theory T is inconsistent if and only if T proves phi for any L formula phi. So inconsistent theory proves anything, and 2, if T proves phi, then there exists some T0, a finite subset of T, so a finite set of sentences from T, such that already this finite set of sentences proves this formula phi. So the second part of this claim is obvious, simply because by the definition of a formal proof, there can be only finitely many sentences from T appearing in it, and so we can take T0 just to be the collection of all of those finitely many sentences. And the first part, that inconsistent theory proves anything, we will leave as an exercise. Now this remark has the following immediate corollary. 1. Let T be an L theory such that all finite subsets of T are consistent, then the whole theory T is also consistent. So this, of course, follows by part 2 of the remark. And second, assume that Ti with the index I ranging over some set I is a family of consistent L theories, and such that we also have Ti is a subset of Tj, or Tj is a subset of Ti for any pair of indices ij in the index set capital I. Sometimes this property is called nested family. So the theories form a nested family. Then, taking T to be the union of the Ti's is also a consistent theory. The reason here is that because of the nested condition, any finite subset of the theory T from which, let's say, we could prove a contradiction, so prove phi and not phi, must already be contained in one of the Ti's. Next, we will establish the deduction lemma, which is very useful in arguing about formal proofs. Let chi be an L sentence, and let T be an L theory, and phi an L formula. Then we have that the theory T union the sentence chi formally proves phi if and only if the theory T proves the formula chi implies phi. Proof. First, note that T proves the formula chi implies phi would imply that also T union the sentence chi proves the formula phi. This is immediate by the modus ponens rules, because we already know that we have phi 0 through phi n a proof of the formula chi implies phi in T. So in particular it is equal to phi n. And since we are working in the theory T together with psi, we can take phi n plus 1 to be the sentence chi, which is indeed one of the sentences of the theory. And so applying the modus ponens to phi n and phi n plus 1, we get the conclusion that T union chi implies phi. Now let us prove the converse implication from right to left. So assume that we are given phi 0 through phi n a formal proof of phi in the theory T together with chi by induction on I. Less or equal than n, we will prove that T formally proves the formula chi implies phi I. So first consider the case phi I is equal to the sentence chi, then it is clear. And also if T proves phi I, then it follows from the modus ponens rule and the fact that the formula phi I implies chi implies phi I is a tautology. In particular, this implies that T proves chi implies phi I when the formula phi I is a logical axiom or an element of T. Because of course in these two cases it would be already provable from T. Next we consider the case when phi I is deduced by the modus ponens rule applied to the formulas phi j and phi k for some indices j and k strictly less than I. So we have that phi k is equal to the formula phi j implies phi I. So in this case, in order to demonstrate that T implies, T proves the implication chi implies phi, it is enough to apply the modus ponens rule together with the fact that the formula chi implies phi j conjunction chi implies phi j implies phi I implies chi implies phi I is a tautology. And of course we are using the inductive assumption on I, namely since j and k are strictly less than I, we are already assuming that T proves chi implies phi j and that T proves chi implies phi k. Finally, we have to consider the case when phi I is obtained by the generalization rule from phi j for some j strictly less than I. So we have that phi I is equal to the formula for all x phi j, and we assuming that T proves chi implies phi j by induction, from which we deduce that T proves for all x chi implies phi j by generalization, as chi is a sentence, and this is the place where we use the assumption that chi is a sentence. In the statement of the lemma, we have that the formula for all x chi implies phi implies chi implies for all x phi is a quantifier axiom namely it is an instance of Q1 and the variable x does not occur freely in chi because chi is a sentence, so it has no free occurrences of any variables at all. So we can conclude that T proves the formula chi implies for all x phi by modus ponens. We have the following corollary. Let T be an L theory and phi an L sentence. Then T proves phi if and only if T union the negation of phi is inconsistent. Proof. So first suppose that T union the negation of phi is inconsistent. Then we have that T union the negation of phi proves phi because any inconsistent theory proves every sentence. So in particular it proves phi. Now from the deduction lemma we get that T proves the negation of phi implies phi, the formula negation of phi implication phi. But since we have that the negation of phi implication phi is a tautology, by modus ponens we get that T proves phi. The converse implication is clear because assume that T proves phi, then T together with the negation of phi still proves phi, because we already have a proof just from T alone, but of course also we can use the negation of phi as one of the non-logical axioms, so T together with the negation of phi also proves the negation of phi, which by definition means that the theory T union the negation of phi is inconsistent. This concludes our discussion in this lecture, and next time we will discuss some further properties of formal proofs, and we will formulate finally Gödel's completeness theorem, and we will begin working towards its proof. Thank you for your attention.